Hello, Honors Chemistry, and welcome to Chapter 8, 8.5, and 8.6, where we talk about advanced stoichiometry, where we take the concept of a mole ratio, right, which we already learned in the previous unit, or the previous section, where it is the relationship between substance A and substance B, right, as defined by the coefficients of a balanced chemical equation, right? So again, the balanced equation only tells you relationships, right, ratios. It doesn't tell you how much you have, right? So going back to recipes, right? So for example, if I want 2 grilled cheese sandwiches, there is no guarantee, even though I have a recipe for it, that I can make 2 grilled cheeses. It's going to depend on how much bread and how much cheese is actually in my house, right? Likewise with a chemical reaction, right? When I have this relationship that says 2 to 1 to 2, right? Those are relationships. I can't make 2 moles of water, right? I can make how much water is possible based on how much reactants I have, right? Which then introduces the concept of a limiting reactant, right? Where, going back to your book, right, it is the one that is completely consumed. If it is completely consumed, how much is left at the end? Correct. 0, right? There is 0 left at the end, right? So completely consumed. And 0 remains, because that's what that means, right, from the other perspective, right? What that also means is that it produces the least amount of product, right? Because if it runs out, then we can't make any more product, right? So for example, if I have 10 slices of bread at my house, but I only have 3 slices of cheese in my house, right? What's that mean? Right, that means I am limited by my slices of cheese, right? For 3 cheese, I could potentially make, for every 2 cheese, I could make 2 sandwiches, right? Which means that I could have a total of 3 sandwiches, right? And I would have 0 cheese remaining. If I have 10 bread, right? For every 4 bread, I can have 2 sandwiches, right? And what does that give me? Right, I could make up to 5 sandwiches. Now, what that says is 5 sandwiches is not real. I cannot make 5 sandwiches. That's not possible, right? I can make 3 sandwiches. I would have 0 cheese remaining. Can I figure out how much bread remains? Correct. I absolutely can, right? In that, I could start from my limiting reactant, because we just defined this as my limiting reactant. It is the one that will be completely consumed. The one produces the least amount of stuff. So now, what I can do is I can start from my limiting reactant. So I can say for every 3 cheese, I would need 2 cheese, requires 3 bread. 4 bread. 4 bread, right? And so what does that give me? Right, so this says 6 bread used, yes? Or we could say 6 bread required, or there are a bunch of words we could put there. But the point is 6 pieces of bread are going to get used. I have 10 slices of bread. So 10, what I have, right, minus the 6 that I used, means I have 4 remaining. Yes, I have 4 that are left over at the end of the reaction. And how much cheese is left? Right, 0, right? That's what the concept of a limiting reactant is, right? So the theoretical yield is the amount produced by, so the amount from the LR, right? Which means that this 3 sandwiches here would be considered my theoretical yield. The amount that I could produce based on my limiting reactant being the one that's going to run out, right? And the percent yield is just the equation, right? But it's the same as every percent, where it's the part over the whole, where the part is the product that is collected, or the amount that is actually collected, right? Over the theoretical yield, the amount I was supposed to produce, times 100, right? Because in real life, things don't often come out to 100%. Now, does all that make sense? I hope so. And if not, so we're going to do practice and we're going to do all of our problems the same way. We are going to go with this definition here, right, where the limiting reactant is the one that produces the least amount of product. Are there other ways to figure out which is the limiting reactant? Absolutely. So we're going to do all of our practice one way, because again, right, if we are consistent, it should sink in better and make it so that way it sticks better in our memory. If you do all of these problems and you do some practice on your own and it's not sticking, come by and see me, right? It's a problem we can fix. We can talk about alternative ways to do it. But if we fix the problem right away, it will prevent big problems later because obviously, chemistry is cumulative. All right, so let's do some practice. Skill Builder 8.4, we've got a balanced chemical reaction. And our problem says that we have 4.8 moles of sodium and 2.6 moles of fluorine. We would like to know the LR, the theoretical, in moles. Now, the and is key because we need to know when do I have to find a limiting reactant, right? Because, for example, these are our introductory level problems, right, from the textbook, which means it's going to ask you stuff like, what is the limiting reactant? Odds are, when I give you practice, I'm not going to ask you what is the limiting reactant. So you need to know when to solve for one. And the answer is this. Every time you know the amounts of both reactants, right? And by amounts, we could say moles, right? So anytime you know the moles or can know the moles of both reactants, you must solve for a limiting reactant first. Yes? Okay. So let's go ahead, right? So 4.8 moles of sodium. So 4.8 moles of sodium. But we also know that we have 2.6 moles of fluorine, right? So this goes back to the sandwich example, right? I don't know if I'm going to run out of sodium or if I'm going to run out of fluorine. So I've got to do a little bit of math and figure that out. What I'm going to do is I'm going to, going back to our definition, figure out which of these makes the least amount of product. So I'm going to get my mole ratio, which says that for every 2 moles of sodium, I could produce 2 moles of sodium fluoride. I'm also going to go get the relationship that says for every 1 mole of fluorine, I could produce 2 moles of sodium fluoride. And then thankfully this math is easy, right? So this one says I could produce 4.8 moles of sodium fluoride. This one says I could produce 5.2 moles of sodium fluoride, right? So again, with words, what this says is 4.8 moles of sodium could produce 4.8 moles of sodium fluoride. 2.6 moles of fluorine could produce 5.2 moles of sodium fluoride. How much can we actually make? Correct, right? This is going to be labeled our theoretical yield. This we cannot make because this is our limiting reactant. And once we have produced 4.8 moles of sodium fluoride, we will run out of sodium. There will be no sodium remaining and our reaction is done. Yes? All right. Concept check 8.3. So consider the reaction if the flask to the left represents the mixture before, meaning that this is our given, right? That's what it looks like. Which flask represents the products after the LR has completely reacted? So we need to look closely at the flask, and it says that I have 2 molecules of nitrogen. It also says that we have what? Right, 3 molecules of hydrogen. Now, based on that, we've got to figure out which is the limiting reactant, how much product we can produce, so that way we can pick the picture that is appropriate, right? So all we're going to do, just like we did in the last unit, is we're just going to take our mole ratios and go, right? So nitrogen, for every 1 molecule of nitrogen, I could produce 2 molecules of NH3, but for every 3 molecules of hydrogen, I could produce 2 molecules of NH3, right? So if we take a look at that, what do we notice? Correct. What's my limiting reactant here? Right, so this is my limiting reactant, right? Because 2 times 2 is 4, so this could potentially produce 4. But over here, 3's cancel, and this one can only produce 2, right? So what that means is I will consume all of my H2. Yes? Does that make sense? consume all of it. So should there be any H2 in the picture when we're done? No, which means we can cross off that one, right? That one is a definite no, because there will be no H2 left when we're done, right? Now, is 4 molecules of ammonia possible? No, right? Which means that this one is a no-go, right? This picture, though, right, has 2 molecules of ammonia, but also that leftover nitrogen, right, which makes that our correct choice, right? Layering all the information together. Make sure you understand this. All right, next up, Skill Builder 8.5. Ammonia can also be synthesized via this reaction. What's the maximum amount of ammonia, right? So here's our goal. In grams can be synthesized from this and this. So again, this is one of those problems where I know the amounts of both reactants. Now, your first instinct might be, but oh, we don't know the moles of nitrogen and the moles of hydrogen, but is that really true? Correct. We know how to get from grams to moles, right? It doesn't require extra information. That's something we already know. So yes, we know the amounts of both reactants. You must calculate a limiting reactant. If on an assessment you have this scenario and you do not calculate a limiting reactant, you will not earn full credit for the problem, right? So be conscientious. Even if you get lucky and pick the right reactant to start from and get the right answer, right? You've only shown half the work for that problem and half the understanding, and you will not get full credit. Okay, what that means is we need to go and figure out the LR. In order to figure out the LR, we need to see which is going to make the least amount of product, because that's what the definition is, right? So we're going to take each reactant, both the nitrogen and the hydrogen, all the way to the product. In this case, there's only one product, the ammonia, right? If there were more than one product, we would just pick a product. Doesn't matter which one. We would pick one of them to take both reactants to. So in this case, we're going to take our nitrogen, convert it into moles, and then we're going to do a mole ratio to get from nitrogen, right? Because that's mole ratio is the only way to do that, from nitrogen to ammonia, and then we'll do molar mass of ammonia. Likewise, we'll repeat and do the same series of steps for hydrogen, the goal being to calculate which of these makes the least total amount of ammonia, which will help us pick a limiting reactant. This says that 25 grams of nitrogen could produce 30.7 grams of ammonia, while 8.42 grams of hydrogen could produce 47.4 grams of ammonia. What is the amount that we can produce? Correct. This is our theoretical yield. This is our limiting reactant. This is not real, right? Meaning that once we hit 30.7 grams of ammonia, we will have completely consumed our nitrogen and the reaction will stop, right? We don't have any more nitrogen. We can't make any more product, right? Do note here, right, it's not like a trick, but this is one of those things where we need to be conscientious, right? Because step 1 is to turn our grams into moles, right? The molar mass of hydrogen is so very small, right, that it actually turns out we have a lot of moles of hydrogen, right? Does that make sense? We have lots of moles of hydrogen, but not very many moles of nitrogen, which is why this math works out like it does, right? Which is why it's important to remember that mole ratios are mole ratios, right? Not mass, right? So everything needs to get to moles first. Okay, next up, 8.6 says we've got this reaction to obtain iron from iron ore. Now let's say you were like, iron ore, what? But here is just, this is a reading problem first, right? So yes, there's chemistry in here, but we also have to pay attention to the problem, right? So we're trying to obtain iron, obtain meaning that it's on the product side. There's my iron, right? Which means that this other compound that has iron in it must be the iron ore. Yes, this must be the iron ore, and this is just the plain old iron, right? So here is got to use our reading skills, right? So the question says the reaction of 185 grams of iron oxide or iron ore with 95.3 grams of carbon monoxide produces this much iron, meaning that this is the actual yield, the amount that we collect. Determine the limiting and theoretical and percent yield. So step 1 is, right, let's figure out which produces the least amount of product. So we're going to start with our grams of each reactant and run them all the way through to our desired product, which is iron. Okay, so this starts just like the previous problem, where we're going to start with our 185 grams of iron oxide, also our 95.3 grams of carbon monoxide. I'm going to fix that in just a moment. And then we're going to go from mass to moles using molar mass. Then we're going to go from moles of each thing to moles of iron using a mole ratio as provided by our balanced chemical equation. And then we will use the molar mass of iron to get 2 grams of iron, so that way we can actually look at which of these two reactants creates the least amount of product. And like I said, this beginning part is exactly like the previous problem because the steps are the same, right? Once you've done it a few times and committed it to memory, it will all get easier. Okay, so if we look at what our work says, right? Our work says that for 185 grams of ore, we could produce 129 grams of iron, but for 95.3 grams of carbon monoxide, we can only produce 127 grams of Fe, which means that this becomes our theoretical yield. This becomes our limiting reactant. And now we have to do the last step, which is to calculate the percent yield, right? And so here, if you're like, oh no, is it actual or theoretical on top? Then we always remember, right? Percents are always piece of the whole, right? Theoretical yield is how much we should make. That is the whole, right? This is the goal. This is what we ought to get. So 127 grams of Fe is what's going to go on the bottom, right? On top, we're going to put our 87.4 grams of Fe times 100. And if we look at what happens here, right, grams of Fe actually cancel, which is part of why percents end up as unitless quantities, right, because we've already got all that built in, right? And then this ends up as 68.8% yield of iron, right? So, like I said, things often aren't 100%, which means that, for example, giant companies where it's their job to extract iron, right, have to bear in mind that for every, they're only going to get 70-ish% of iron from the ore that they work with, right? And that's what a lot of industrial chemistry goes into, right, is how do I maximize these reactions and the systems that are doing it so that way we can hopefully get as much as possible, right? Because obviously that's the goal for a company. That's where they make their money, right, is by getting as much as possible out of every reaction. Okay, next up, concept check 8.5, right? It says ammonia can be synthesized by the reaction of nitrogen monoxide and hydrogen gas. We've got a balanced equation. A reaction vessel initially contains, right, so that's how much is in there, some 4 moles of NO and 15 moles of H2. What is in the reaction vessel once the reaction has occurred to the fullest extent possible, right? So what do we got to do? Right, all this is a limiting reactant problem, right? Saying that we would start with our 4 moles of nitrogen oxide and nitrogen monoxide and 15 moles of hydrogen and let's just figure out one of our products, right? And let's pick one. Doesn't matter which. So let's start with NH3, right? So NO says that for every 2 moles of NO, right, we could produce 2 moles of NH3. Right, which means that hypothetically we would get 4 moles of NH3. For 15 moles of H2, right, we would take our 5 moles of H2 from the equation, right, and we could make 2 moles of NH3. And what's this going to give us? Right, 6 moles of NH3. What does that mean? Right, that means this is not real, and this is our theoretical yield, and this is our limiting reactant. So what did we just learn? How much NO will be left at the end? Correct, 0, which means that we have just narrowed the answers down to these two because these both say 0 NO, right? Now, if we continue reading, B says there will also be 0 H2. Is that how this problem looks? No, right? There will clearly be excess H2 left, right? Because they're not stoichiometrically equivalent, which means that this one cannot be correct. If we continue onward, right, it says 4 moles of NH3. Ah, that's right, and which means that this must be it also, right? And that's it. That's that problem, right? Okay. Oh, and that's the end. All right. Thank you for listening. Be good, and I will see you soon for 8.7, where we talk about one last conversion factor from this unit. All right, be good. Have a great day, and I'll see you soon. Bye.